So when you come back on Tuesday, right, we can actually start chapter 26, okay, and we'll see how that's going to happen without Canvas. Yeah, chat.
When will the group work from yesterday or Tuesday be?
So just hold on to your group work. I have been receiving them, but I have the problem is that I cannot grade them anyway because I cannot get on Canvas to give you guys points for them. But Mastering Physics does keep track of your points for now. So I think the only thing you need to really deal with that has a due date is the Mastering Physics homework, okay? Right. And Chapter 25 homework is pushed back to due on next Thursday, so you don't have to worry about it this weekend, okay? All right, so just focus on getting the exam, studying for the exam for Monday, okay? Any other questions before I get started or comments? Push that down. Okay. So the last section of this chapter is, we're just going to kind of talk about it conceptually because there's just, as usual, the problem gets more and more complicated, right? If you put more and more charges around your system, right? So remember that when we had multiple charges, there was this complicated equation where, right, I'm going to do the example once again where we're just bringing the charge in from infinitely far away along the x-axis. That way we don't have to deal with the three-dimensionality of things. But in general, you could have a three-dimensional situation where the first charge, right, you get for free, right? The amount of energy that takes to do that is free because there was no electric field that's going to be opposing you, right? But, right, once you get to charge number 2, right, you're going to have one force that you have to deal with, right? That's going to give you one term in the potential energy from between charge 1 and 2, right? So U1, 2. But when you bring in 3 charges, right, let's say charge 3 is here, right? Not only are you being opposed by charge 1, you are also being opposed by charge 2, right? So now you have the potential energy from 1, 3 plus the potential energy and 2, 3, right? If you bring the 4th charge, it's actually going to be 6 terms in this summation, right? The general way to write that is this complicated summation equation where, right, where you sum over, you know, the charge 1 and then charge 2, 3, 4, you know, all the different combinations of charges, and those will actually give you all the total potential energy for you to do that, okay? So, right, if we're talking about potential slash voltage instead of potential energy, as usual, we just, you know, delete, you know, well, not delete, we just divide by one of the charge. In this case, we're going to divide by charge J, right? When you divide by charge J, the charge J actually cancel each other out. And therefore, the potential or voltage, right, that you can calculate for multiple charges is actually much simpler, and this is actually much more useful compared to the potential energy, because now you don't have this double summation thing, right, where you're summing over I and summing over J. You're actually just summing over all the different charges that exist, okay? That gives you the potential slash voltage, okay? Right? So this is much better, much easier to calculate, okay? And if you talk to any of my electrical engineering or computer engineering also colleagues, right, they would use, this is why voltage is a much more useful quantity compared to electric potential energy, right? It's just computationally, it's like exponentially harder to calculate the potential energy versus just calculating the potential, okay? Just because you have this double summation situation with the potential, right? Right. Okay. So you can calculate the potential for a very complex system. So let's say you have 2 charges here, right? You can draw these things called equal potential surface, which is the contour line. Remember, the idea is that anywhere along this green dotted line, right, this one particular circle, your potential is actually constant. So it's kind of like on a hill, like where you're walking on a constant elevation as opposed to climbing uphill and downhill. right? On top of the hill, of course, is the big positive charge, right? That's the top of the peak, right? If you have a if you have a hole in the middle of on the planet, right? Negative charge, pretend it's just like an infinite hole that things are going to fall into, right? So this is on the right hand side, it's kind of like a three-dimensional view of this, where you can see this plotted here is the x-axis, right, and the y-axis. But then the vertical axis is not, z. It's basically how high the voltage gets, right? When you're near the positive charge, it basically goes to infinity, right? And then the negative charge is just kind of like an infinite hole that, charges can actually fall into. Okay, so it's more of a graphical view of this. Okay, one of the things that you not medical professor can measure is actually this thing called ECG, the electrocardiogram, or EKG, depending on which country you're from. I think if you're in Germany, I think cardio starts with a K, that's why they call it EKG. The idea is that, if you want to figure out whether your heart is working well, right, the muscles of our heart is actually controlled by, some part of our brain that I don't know, right? But the way it controls it is that you're sending electrical signal to the heart from your brain constantly. Okay, pump, 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 As soon as that signal stop, you're in trouble, right? So you can actually measure this, and this is an electrocardiogram. And you can actually find these equal potential surface. Remember, the equal potential surface is where the voltage is the same along that line. Okay? And you can actually see this, and I'm not sure which one is positive, which one is negative. I think this is probably the positive side. So as the heart pumps, this actually oscillates up and down, blue and yellow, because one side of the heart has to contract, the other side has to relax. This side, the other side of the heart has to contract, the other side has to relax. So there's this synchronicity that you have to deal with, right? If both of them contract, all the blood just squirts out, and that's not a good idea, right? So these are actually equal to potential lines that you can see in someone's heart, and this is how basically, if you know anyone who has a pacemaker, right? A pacemaker is basically just they attach it, I think, around like the side of your chest or something like that. It's basically sending this electrical signal back and forth to basically control your heart pumps. How the rate that your heart is pumping. Okay. So I'm not going to. There's multiple examples in the textbook, but don't worry about these for this week. But it's definitely useful after you finish the midterm, and after you finish midterm 1 on Monday, to start studying these examples in the textbook, and hopefully that'll bring us to the end of chapter 25, where we have this idea of potential energy, right, by bringing charges near each other, right, and also a simpler version of potential energy. Sorry, it shouldn't be, it's not a simpler version. A way to simplify the problem, instead of trying to calculate potential energy all the time, you can just calculate this thing called voltage or potential, which is easier to calculate, okay? You always want to use voltage whenever possible, okay? And then after you find the voltage of a particular system, just multiply by whatever charge you put there, right? And that'll convert it to potential energy for you, okay? So that's what's nice about it. Okay, any questions about chapter 25 before I jump into the review problems that I want to go over today? Okay, I'm going to stop the video so it's actually